Oh my goodness, I can't believe we're doing such easy stuff again. I love this stuff. Or, wait a minute, how do we do that again? Here's why. You guys know how easy stuff is. Can somebody explain to me what direct variation is? Right? Chapter 2. Piece of cake. Direct variation. Everybody knew what they were doing, but it's too easy. So our brain says, I don't need to remember that. Pushes it right out the side, drains right on our pillow. It just does. So we're talking about variation again today, and unfortunately, when things are too easy, we can tend to lose them a little bit. So, yeah.
Starting the overall chapter, they're like pretty decent overall chapter.
Most students really like this chapter when we get to the point where it's going to be doing a lot of factoring. And most students feel really good about factoring. So this is generally a pretty good chapter. All right. Yes, because again, most people feel pretty confident with their factoring skills. All right, this chapter, chapter 8, make sure you put your name on your packet, by the way. It is kind of a thick monster. And we haven't had time to talk in our PLCs recently, which, you know, Jake would hear if he didn't have his phone. We would talk about whether or not we're going to split this one. I'm not certain about that yet, so I can't give you a yes or no. We cover inverse and direct variation in chapter 8. And then we start talking about graphing. And then it kind of switches gears into the whole factoring business. And so there is a split there. It's just if everybody wants to split up that test and have it taken half at a time or not. So we have to discuss that. So rational functions, the root word of rational freaks people out because it's ratio, which means fraction in math. But these are some pretty cool and basic relationships that we see with division. It's what we need to study. So rational functions help explain how surface tension allows some animals to tread across a pond's surface. There are animals that walk on water. Mosquitoes can walk on water. In fact, they lay their eggs on the top of water. And that's because they're so light and they have such a large surface area that it just sits on top of the water. It's almost like a little cup that the water forms. Because the surface tension is what holds water so that you don't get wet. That's what happens. But once you fall through the water, then you get wet. Now there's good and bad for that, because one of the things that they can do to spray for mosquitoes is spray it on top of the water, because that's where they are. So they can get mosquitoes. But if you ever see a mosquito on the water and you're careful enough, you could go bloop, and it'll go into the water and you'll drown. See how I feel about mosquitoes? Any of you, one of those people that have the most sensitive skin in the world, and you get a mosquito bite and it's like annoying? Yeah, I can't stand that. So mosquitoes are not my favorite. So they cannot break the surface tension because their surface area is proportionally not heavy enough with the surface area and the tension to get them through. Now it says, how are we going to graph rational functions and solve rational equations? That's what this chapter is all about. But we're going to start, and there's a lot of blank space here on the front for you, by reminding you what direct variation is. Direct variation, really sweet, easy little formula in chapter 2. Y equals kx. Direct variation can explain, you go to the movie theater, big sign. Everybody pays $7 all the time. So you go to the movie theater and you have said, tonight I'm paying. And you look and it's you and 3 friends. So 4 times 7, hey, I'm going to owe $28. And you know it because you understand every single ticket costs the same amount. So for the movie theater, this variation equation would be y equals 7x because they're charging $7 per person. A real dollar store, back in the old days when they didn't put a little tab on some of them that say $1.25, a real dollar store, and you would know how much you're going to pay except maybe for tax. I picked up 10 things, hey, that's $10. That's how it worked. So direct variation is just that really basic, all I have to do is multiply to get the answer equation. And today we're going to talk about direct and inverse variation as we go through this. So in 8.1, our new focus, because direct variation technically is inverse variation. And what we want to do is recognize and use it. Well, if you multiply, really basic, and you get direct variation, inverse variation comes from a division relationship. So, if you buy more tickets at the movie theater, you have to pay more money. As your number of tickets goes up, the number you have to pay goes up. Inverse variation is about what happens when one of them goes up and the other goes down. You buy your new car. Your car starts to age. It gets older and older and older. Its value goes down and down and down. One is going up, the other is going down. So we needed something to cover that really basic division relationship. That's going to be inverse variation. So we're going to recognize and use inverse variation. And tomorrow we'll start talking about joint variation, other variations besides just direct and inverse, because there's tons of them. It's just that we don't want to cover them all in one sitting. So it's spring in Minnesota. This is a problem that probably you've got a pile of something sitting in the yard right now. Your parents are saying, look at all those rocks. We've got to get those back over there. This is mulch. To decorate, do a little landscaping. You have 20 bags of mulch. There they sit. You plan to spread the mulch from all the bags to make a rectangular layer that's 3 inches thick. Okay. So you've got some kind of rectangular area. Maybe it's right next to the sidewalk. You're going to make into a big, nice pile of mulch. But you're going to have it be 3 inches in depth. So you've got your plastic down. You want to pile mulch on it. You want to pile it on 3 inches thick. It says how many square feet could you cover? If L and W represent the length and width of the rectangle in feet, what equation could we use for this? Well, this is three-dimensional. This is volume. So we would need length times width, and I'll put H for height, but really it's going to be depth in this problem, is the volume. And here's what we know. Each one of those little bags over here says it's going to cover 2 cubic feet. And you got 20 of them. So that's going to give you 40 cubic feet of volume. We also know this. They messed with us and put that as 3 inches on purpose. The rest of the problem is in feet. You can't leave 3 inches when the rest of it is in feet. So we have to put 3 over 12, and we have to think of that as 1/4 of a foot. Now this problem is not something we're supposed to get at. This is the right answer to. We're just supposed to come up with different things that could happen. So now, if I divide by 1/4, it's the same as multiplying both sides by 4. I would get LW equals 160. That means I have options. If I come up with any two numbers for length and width that would multiply to 160 or less, I will be able to cover this. So I could say I'm going to have a length of 2 feet, 2 of these tiles right there. Well, if I do that, I could get 80 feet lengthwise, and it would work. But we don't know those numbers, so we just have to say, hey, this is what you can get. You know? So if you decide you're going to have 4 feet, I guess that'd be kind of wide for a sidewalk. Keep looking at the tiles, because everybody knows these are 1 foot by 1 foot, right? So if you go 4 feet, maybe place some sidewalk there. Then you could go 40 in this direction with the mulch, and you can make it happen. So this is, like I said, it's a perfect example for spring in Minnesota. You know, as soon as we get rid of the snow, fortunately, we didn't get any of that stuff. St. Cloud did, but we didn't. Jake, you don't need to check on that on your phone. You can put that away so you can pay attention. Essential understanding is if a product is constant, if we multiply two things together and we always get the same thing, then that means a decrease in one accompanies an increase in the other. As one goes up, the other goes down. That's how it works. Now, direct variation was a beauty. Y equals kx. Nice little equation. Worked really easily. But our job is always to find k. That's what we need. X and y are part of the equation. They are not going anywhere at all. We need to find k. And now for inverse, which in some books they call indirect variation, just so that you've seen that before. Inverse and indirect mean the same thing. Y equals K over X. So, notice K is not 0, because that's talking about, hey, we're going to go to the store where everything's free, and somebody says, how much are we going to have to pay? Well, it's free. Okay. It doesn't make any sense. Oh, slider back up. Okay. So, relationships where both of them go up are direct. One up, one down, inverse, indirect. And we have to recognize these. And we have to know which one is which, and how do we write them. That's our job. Find K and write it. So, like it says here, let's just get a head start on it. If it's direct, and it's Y equals KX, and we have to find K, well, we might as well solve for K right now, so we'll know what we have to do. We would divide both sides by X. Here's what's weird. So if we want a direct variation equation, which is multiplication, we have to divide to get it. Of course we do. It's like undoing it. You know, we're trying to do the inverse. So if we want K, we're going to have to divide. But for inverse variation, if we want to find K, we're going to multiply both sides by X. Again, it's like we're undoing it. Inverse is about division. But to go backwards a step and find K, you're going to have to multiply to see. So this is going to start us off where they're not going to give us the fact that it's direct or inverse. They're going to ask us, is this a direct or inverse relationship? And they're going to give us X's and Y's. So this is what we want to check. If we take the Y and we divide it by X, and every time we get the same number, then it's direct. If we multiply the X's and Y's together, and every time we get the same number, then it's going to be inverse or indirect. So that's how we'll know. When two quantities vary inversely, as one quantity increases, the other decreases proportionally. As we finally get some decent weather in Minnesota, if you stood outside the front of the school, the number of people wearing jackets will go down. That's just what happens. It's Minnesota. You like it when the weather even gets up to 50. People wear shorts when it's 50. Yeah, that's just how we are. So it's one of those things. Now K is still called the constant of variation. It was in chapter 2, and it is now. We're not going to change the name of that. So that's the $7 per person at the theater, or the $1 for each item at the dollar store. Constant of variation. Now, people have trouble with that name because they're like, isn't that an oxymoron? It says it's a constant. Constants aren't going to change. And then it says a variation, and vary means it's going to change. Well, the X's and Y's in the equation change, but K doesn't. K is a constant, so it's a number, we want to find it. All right, away we go, from start to finish. We have some data. There's little X and Y. They want to know, is the relationship between these, is it direct? Is it inverse? Maybe it's neither, because not every relationship is direct or inverse. And then write a function that models that. All right, so I come over here and I tell myself, let's see, direct is Y equals KX, so they gave me X's and Y's. I want the X's and Y's together. So if I take Y and I divide it by X, and I get the same thing every time, then it's direct variation. Then, if it's inverse or indirect, Y equals K over X, and I want to see how X and Y behave together, I have to multiply both sides by X. Okay, so if X times Y comes out to be the same thing every time, then it's inverse. So that's what we're going to do. You ready? All right. 15 divided by 2. Well, let's do these in decimals so we can see are they exactly the same. is 7.5. 7.5 divided by 4. 1.875. It's not correct. It has to be the same number. Not even close. Well, then let's try inverse. X times y. Let's see, 2 times 15 is 30. 4 times 7.5. 7.5 and 7.5 is 15. Double that. Oh, yeah, we get 30. 3 times 10 is 30, and 2 times, well, there it is. It's inverse. That's what it is. And what we just found is k. So we go over here and we say inverse is supposed to look like this. Y equals kx. Y equals 30x. Over x, I should say. There it is. So we find k by taking x times y for inverse variation. We find k by taking y and dividing it by x for direct. Oh my goodness, I'm just going to come around and grab the phones and jail them up. Enough's enough. Too many of you. You're not that good at hiding it. You think you are, but you're not. Yes. So, put them away. B. We're going to do the same thing. We're going to think, okay, if it's direct variation, when I divide, I'll get the same thing every time. If it's inverse variation, when I multiply, I'll get the same thing every time. Okay, let's go to this one. Direct. Y divided by x. Let's show it's direct. 10 divided by 2 is 5. 8 divided by 4 is 2. Do I need to keep going? This is not direct. It has to come out to be the same thing. Okay, let's try inverse. Inverse was x times y. Let's see, we've got 20, 32. It is even. By 4. It doesn't mean there isn't a relationship there. Very well could be there is. It's just that it's not direct or inverse. There's all kinds of relationships out there. It doesn't have to be direct or inverse. So that's all we're studying today. We say neither, and we walk on. You know, we go on to the next one. Done. Can't do anything with it. It's not direct or inverse. Well, no. So now we have some more tables. But we know what we're supposed to do. If it's direct, when you take y and divide it by x, you'll get the same thing every time. If it's inverse, and you take x times y, you'll get the same thing every time. Go ahead, use your calculators for A. Tell me what you think, and then we'll write an equation. Direct or inverse? Direct. So you did your division. What'd you get every time? All the way down? Excellent. So it's y equals 40x, and it's direct. Left or B, if you haven't already. I know some of you are cruising through these. fun. What do you get for x times y? 8. So y equals k over x will be y equals 8 over x, which is inverse. Yeah, the last one. I do the same thing. It's actually direct variation. Multiplying the same thing is actually inverse variation. See a lot of neithers written down for C. Agree? Yeah. Again, just because they're not direct or inverse doesn't mean there's not a relationship. It's just not the relationships we're studying right now. So we'll just write neither and move on our way. There wasn't any one number that showed up when you did the division or one number that showed up when you did the multiplication. So you move on. Because there are other ways to do this. Pure algebraic in this case, they're going to give us stuff. They're just going to hand us things. But what we always want to find is k. That's our job. So this says, suppose x and y vary inversely. They just handed me that. Look at it. As soon as I see that, in my head I'm thinking y equals k over x. I usually write it down. Well, I need k. Well, they gave me help for that too. It says x is 4 when y is 12. You give me one step and we can get k. What's k? 48. Multiply both sides by 4. Well, that's all we needed to write our equation. It's y equals 48 over x. There's usually a follow-up with these, and there is one over here. It says, okay, you wrote this beautiful formula. What would y be if you put 10 in for x? Well, that's not toughy. Now, if you want to, you could reduce it, but I think I remember last year, your book likes decimals for this stuff, so just 4.8. That's the division right there. So if they give us x and y, fabulous. We'll put them in the equation and we'll get k, because that's what we need. Now here's the really cool part. What happens if we graph this? Remember, that's what we had right there. Y equals 48 over x. Well, I don't know about you, but I'd rather not put a 1 in there and have to try to graph 48. So start thinking about nice numbers that would be like between -10 and 10. Look at 48 and 8 pops right into my head. Because if you divide 48 by 8, what do you get? All right, so I got a positive number. I'm going to cheat and also put it in as a negative. So put -8 in, what do I get? Aha! So 8, 6. 1, 2, 3, 4, 5, 6. Whoops. And -8, -6. Huh. Oh, wait a minute. That can't work. Because there's a number we can't put in there. Well, then that can't work. That must mean it's not a line. Well, we've never done this before. We better take a peek at it. Let's see this. What could this, if that's not a line, what on earth are we supposed to do with it? Let's see. Y equals 48 divided by x. Zoom 6. Oh, look at that. That is cool. That is called a hyperbola. A hyperbola with two branches. So what happened was we have one branch for the negatives and one branch for the positives. And if I put, I had negative 8 in there before, if I put negative 6 in here, I can get negative 8. And I can draw the left branch. And if I go over to the positive one and say, well, I did 8 before, how about if I do 6 and 8 this time? 6 and 8. And I have the other branch. Now, I just have to explore the coolness of all this for a second. Excellent. Well, you know what would be really super cool? If I could get this same stuff to show up here and here. I mean, what a cool pattern would that be? I think we know how. If I want this to show up down here, what should I plop in front of it? Negative 48 divided by x. Negative 36 divided by x. Negative 16 divided by x. Negative 4 divided by x. I have to show you the coolness. I just had to. Now, what did you notice about how it graphed and the numbers that I had in here? You see how it moved closer and closer to the origin as the number got smaller? Let me see what happens if I just do like x over 2 and negative x over 2. Or the other way. Negative 2 divided by x and 2 divided by x. Add her upside down. So if that number that's on the top gets smaller and smaller, it brings it closer and closer in to the origin. Very cool pattern. Very cool. So this is called hyperbola with two branches because it had one in that lower left and one up in that upper right up there. That's what you get when you do basic division. Very cool stuff. So this one says, let's start over now. Suppose x and y vary inversely. X is 8 when y is negative 7. What's k? Negative 56. So let's put it back in. Now, what did we say about where these were going to show up if it was negative on top? Yeah. So the first one we did was positive. It was quadrant 1 and quadrant T. If you remember your quadrants, quadrant 1, 2, 3, and 4. But with a negative, it should be here and here. Well, let's check it out. Give me a nice set of numbers between negative 10 and 10 that you know will multiply to 56. 8 and 7. So let's use 8 and 7, 7 and 8, negative 8, and, oh, I forgot my negatives. Because when you take 8 and divide it, you'll get a negative 7. That doesn't get the 7. And 7, negative 8. And then negative 8, 7. So we can get some negatives. Negative 7, 8. Let's make sure those show up in the quadrants we know they're supposed to. 8, 1, 2, 3, 4, 5, 6, 7. And 7, negative 8. Right there. Negative 8, 7. and a negative in front of it. That's what's supposed to happen. So, B says, what does the graph of this function look like? Well, like I said, it's our new name. It's a hyperbola. If you didn't know that, you'd probably just say, well, it looks like it's got a little parabola up there in quadrant 2 and another little parabola down there in quadrant 4. It has those two branches. And then C says, how about if you put 2 into this? We wouldn't want to graph it. But what would you get if you put 2 in there? Negative 28, yeah, we wouldn't want to graph that. So for C, negative 28. Good stuff. Hyperbolas. You could probably take 4 different classes in college just about hyperbolic functions. There's a ton of things to learn about. So now, we want to talk real life. We want a relationship where as one thing goes up, the other goes down. And what they're using is this. The more people you have help with the job, the time that it takes to do the job goes down. That makes perfect sense as long as, not everybody's working on something really teeny. So this says your math class has decided to pick up litter each weekend in a local park. Good for you. Each week there's approximately the same amount of litter. Unfortunately, people are littering all the time.
So this can be used for
Oh yeah. Yeah, these relationships, well, they're really basic relationships, but they absolutely could be used. The table shows the number of students who worked each of the first 4 weeks of the project and the time needed for the pickup. Now, I don't know about you, but I'm sitting here thinking, the more people I get, the less time it's going to take. That's an inverse relationship. So, it should be y equals k over x. But these are x's and y's. So I want to see how do these two work together to give me k. Which means I better go ahead and multiply them all so I can figure out what k is. Let's see. 3 times 85. 255. 5 times 51. 255. 21 times 12. Oh. 15 times 17. Oh, man. Well, we won't be able to use this for inverse relationship. Look at 252 is so far away from 255. You don't do that in real life. In real life, you say, oh, this must have been the day that Jim was here. He had to leave early, so he picked up his trash really, really fast. Let's just use 255, because that's what had happened on most days. And that's usually what happens. So, yeah, because it's people. People do things that mess up systems. We just, So we're going to use the 255 because we know most of the time it's 255. So K is 255. So the function that models the data is y equals 255 over x. Except, if you look at this, they didn't use x and y. They wanted us to use n and t. The variables don't really matter, but when you're reading a word problem, it kind of helps. Because n will stand for number of people, and t will stand for time. So, it might be a little helpful for you. So this one down here says, let's follow it up. We've got our nice little formula. I have to because they're going to start giving us the variables. So if they don't tell us that we can just use x and y, we have to use whatever the variables are. I know. It's supposed to be really basic and easy, and then they do that. It is fun. It is. How many students? People come up to me and say, you know what, I would volunteer, but the last 3 times I've done this, you guys have gone over 30 minutes, and that's all I have. 30 minutes, that's it. If you can get enough people together so that we can do this in 30 minutes, I'll be there. So, you need t for time to be 30. That's what you need. Fastest way to do this is just going to be to slap a 1 under there and cross multiply. So 255 divided by 30. Boy, you can't get 8.5 people to go. You do have to get 9, because remember, they want it out of there at 30 minutes. So our calculator tells us 8.5, but this is people, and if they want to be out of there in 30 minutes, they better get 9 people. Isn't going to happen if they go down 8. Now, this one says, we really like picking up things. After a major storm, your math class volunteers to remove debris from yards. Good for us. The table shows the time t in minutes it takes the group of n students to remove the debris. Well, it's the same thing. If we get more students, it should take less time. It should be y equals k over x. But we have to find k. Chances are these aren't going to be exactly the same every single time, but 225 times 1, we can do that in our noggin, right? 3 times 75, maybe? We can do that in our noggin? Think quarters? That's 225. 45 times 5. And here comes our spoiler. But it's so close. So we say, you know what? We're going to 225 this one better. And again, he didn't want us to use x and y. He said, all right, we're going to do n and t again. Okay, n and t. B says, oh, they got to leave earlier this time. 25 minutes. At most 25 minutes. All right. So 25 equals 225 over n. Let's slap our little 1 up there. Oops, it's a B, not C. And we get 25n equals 225. How many quarters in $2.25? Exactly 9. It is, because we didn't put 30 minutes in this time. We found out exactly how many it would take. 4, 3, 2, 1, 0 me. I mean, this is what we did today. This is inverse variation. So, how comfortable are you? Good, good, good. Looking like some maybe 3.5. Some people are 3 in me and then 4 in me there. So that is good. Now, if you haven't figured it out yet, I am absolutely right about homework. If we don't do enough homework, it will not stick. Some of you have taken a giant homework vacation over the last couple of chapters. 28 days counting today. No more vacation. This can be a really good chapter for you.
It's so nice and warm.
It's not beautiful outside right now.
But once you get can we opt out of taking a final?
No. Multiple choice.
I don't want to take it though.
Why?
Because I don't want to take it.
Well, that's not a good reason.
What's multiple choice? Nah, but like, what if I get my grade to somewhere I think it's okay? I don't want to mess with it. Like, I don't, like, I'm okay where it is. Like, I'd rather
You'll have to take
the
it.
possibility of not going up.